So today I'm pleased to have Noah here, and we are we are going to listen to Noah about his recent work on the role of adaptivity in when you are doing decoding, and and Noah has been working on quantum error correction and other topics at University of Maryland, and at the moment he's working with Daniel Gottsman, and today he will discuss with us his findings. So, yeah, like Noah, would you want it to be interactive, or do you want questions towards the end? Like, I mean, it's very much the choice of the speaker.
Yeah, I'm fine with if anybody has any questions in the middle, you can just
Very,
stop
very
me and
nice.
get them out of the way.
Okay, so in that case, just unmute yourself and ask, when you have some question or something, or type in the chat box. And Noah, maybe you could, start the screen sharing, and yeah, the stage is yours. Yeah.
Thanks. All right. So everybody can see it. Great. So yeah, thanks. Thanks for the introduction. Thanks for inviting me to give this talk. Pretty excited to tell you all about what we've been working on over here in Maryland. Me along with these co-authors, Sam, Eric, and Daniel. We just put out this recent work on adaptive syndrome extraction, and here's the archive link in the bottom. So the overall motivation for this work was essentially the idea that the quantum error correction itself is noisy. So when we do error correction, we have to apply these gates and measure these stabilizer generators. And applying gates on the system has the potential to introduce some noise. So in particular, we apply some 2-qubit gates or single qubit gates, or even just let the qubits sit around, then they're going to accumulate noise over time. And so in doing so, we might introduce some errors just by attempting to measure these stabilizer generators. Now, this isn't an issue theoretically. If we design our gadgets to be fault tolerant, then our code should be good enough to correct any residual errors that we might introduce. But it still is kind of unfortunate that this thing that we're doing to correct the errors can sometimes actually introduce them. And then a little bit more specifically, on some devices, it's much more advantageous to just let your qubits sit. So the idling error rate is like much lower than the 2-qubit error rate. So in that case, we are more advantageous to just let the qubits sit and then maybe do some logical gates, as opposed to constantly interacting with the system and performing syndrome extraction rounds. So the idea, I guess, is maybe we should minimize the 2-qubit gates in particular, but just touching the encoded system at all. So there's really maybe 2 ways that you can do this. You can either just do less frequent QEC, so we just don't try to correct errors as often. This can have issues, obviously, if we let the errors build up. And then what we're going to talk about later in this work, or I guess the entire point of it, is that maybe we can only measure a subset of the generators, and in particular only the stabilizer generators that are useful in some sense. And I'll go into what useful means in this context. So here's a picture of a service code and some errors. And suppose that we knew where the errors were, but we don't really know what they are. So they're kind of treated like erasures, but let's just play along that they aren't erasures. So ideally what we would do is we would measure only the stabilizer generators that interact with the qubit that has the error. So on this right side, I shaded some of the stabilizer generators, and these are the ones that really we should measure, because these are the only ones that tell us some information about the error that we can then use to correct. Any of the other generators, they're just going to give us a trivial syndrome because they don't interact with anything that has an error. So, if we didn't know where the error was, then that's good. We can figure it out. But given our priority knowledge of where the errors are, then this is just kind of useless information in this region. So in the extreme case, suppose that we have a system that doesn't have any errors that we just knew, then it makes sense that we just shouldn't touch it at all, because there's no error, we don't have to correct anything, so doing syndrome extraction can potentially introduce more errors than there currently are, which is 0. So this is perhaps oversimplifying what needs to happen, but we only want to measure the generators with the support on the error because these are useful in some sense for decoding. They're going to tell us something about the error. And this kind of extends that we shouldn't touch qubits that don't have any errors because we don't want to introduce them. Now, like I said, we of course don't know where the errors are in general. If we did, it would be much easier. For example, an NKD code can correct d-1/2 arbitrary errors, but we can correct double that if they're erasure errors. So knowing where the errors are is a big help in decoding. But again, we don't know where the errors are, so what are we going to do about this? So the strategy we introduced with this adaptive syndrome extraction scheme is this detect then correct. So on the left, we have the same surface code, and this time I've added some of these larger checks. So these larger checks, you can interpret them as telling us whether or not there's an error in the region. So they're error detection checks. And we're going to measure these error detection checks, and if one of them has a flag, the stabilizer measurement turns out to be -1, then we know that there's an error on one of these, say 9 qubits in this region. The other regions didn't flag, so we know with some certainty that they don't have an error. So on the next step, we can't quite fix the error because it's just error detected, but then we go in and measure the stabilizer generators that are useful for correcting whatever errors in this region. So on the right side, we go in and we measure, these highlighted stabilizer generators of the surface code. And with that, we can then correct the error, whatever error is in this region. And we don't have to touch any more than we had to measure these error detecting stabilizer generators, the rest of the surface code. So with that out of the way, that's our big picture, and then I'm going to go into exactly how we accomplish this. And here are the building blocks that we're going to do. So the first thing we need are these iceberg codes, and these are also known as quantum parity codes. They were introduced a long time ago, almost the first codes, and then they were sort of recently extended to larger sizes. They're a family of error detecting stabilizer codes, and they have 2 generators. They have Z on all qubits, and then the poly X on all qubits. And with these 2 stabilizer generators, that gets us a code that has n physical qubits encoding n-2 logical qubits, and has a distance of 2. So the distance of 2, of course, means that it can detect 1 error, and it can correct no arbitrary errors. So as such, it's an error detecting code. And specifically in our paper, we look at this 422 code, which is the smallest error detecting code. And you might be asking, why is it an iceberg code? It's because if you draw the logicals of this code, which are just weight 2 checks, that go between this sort of shape with qubit 1 and then qubit n. If you color it in the right way, it kind of looks like an iceberg. So just to go a little bit more into detail about the iceberg code, like I said, it has 2 stabilizer generators, X's in all the 4 qubits, Z's in all the 4 qubits, and it encodes 2 logical qubits. So we have these 2 logical representatives, these X1, Z1, X2, Z2, and they are given by this sort of shape where they overlap, of course, on the logicals between qubits. So it can detect a single error, and technically it can correct a single erasure error, but we don't really make use of this in our work. So then the other piece of our construction are these hypergraph product codes. And there's been a lot of work done on these hypergraph product codes, which are a CSS type code, from taking the graph product of 2 classical codes. And if you have a classical code with NKD parameters, then the resulting quantum code has this resulting parameters, essentially n squared, k squared, d. And like I said, there's been a bunch of papers on this from decoders to logical gates, circle level performance. And in particular, there's been a lot of focus on these quantum expander codes. So these quantum expander codes are essentially, or you take the graph product of 2 classical expander codes to achieve a quantum expander code. And these have really nice parameters. They have constant rate and a distance that scales like the square root of n. So just like the surface code. And they also have good decoders and nice logical gates and single state prep, just a whole bunch of things that makes it nice. And then the second sort of subfamily of hypergraph product codes we're going to look at are these lacrosse codes, which are formed from 2 cyclic codes. So the seed codes are cyclic. Now I want to mention that while we use hypergraph product codes as this second layer code, as I'll soon mention, any QLDBC code or even stabilizer code, I guess, could probably work just as well in our construction. So what is our construction exactly? We're going to take the 422 code and we're going to concatenate it with this hypergraph product code. So what this means is we have a whole bunch of blocks of 422 codes, each encoding 2 logical qubits and 4 physical qubits. And if we have a whole bunch of blocks of these things, we end up with a whole bunch of iceberg logical qubits. So then what we do is we're going to construct enough blocks to that we have enough iceberg logical qubits to act as physical qubits in our hypergraph product code. So the logical qubits on the 422 codes are going to act as these physical qubits on the hypergraph product code. And to do this, we have to assign logical qubits to physical qubits in the hypergraph product code. And this is actually a pretty big detail that you need to.
So Noah, can I ask a question?
Yes.
Yeah. So it seems like, so you basically the idea is that you're saying that, it would be better to know where the error is. And then if you know that, then, just touch that region and do your correction and don't touch other region. And to know where the error is, you are using an error detecting code, but the error detecting code cannot correct. So you are concatenating with a code which can correct. So in this case, you are using a hypergraph product code and you are trying to use that to, error correct. But I was just wondering that, let's say when you do this concatenation, then the number of, let's say, so in one case, let's say if you had just done hypergraph product code based, syndrome extraction, then in that case, you would have ended up measuring too many, checks, which can be like large weight checks also. Here, what you are doing that using this error detection code, you are, measuring small weight checks and you are just doing error detection. You are not doing error correction. But the problem here is that maybe, the number of measurements that you need to do to do error detection, because now you are doing this concatenation, right? So would that increase the overhead in number of measurements? Let's say, I mean, the error detection will become costly, maybe.
Yeah, that's a good question. So later I'll talk about sort of the cost of doing this. We kind of quantitatively show that you do get a decreased cost in terms of gate count by doing the scheme. But you are correct that specifically the number of measurements that you have to do doesn't decrease all that much, because you have some number of so because you have some number of measurements that you have to do for these iceberg codes, and then you still have to do some for the hypergraph product code. So in total, you're still doing around as many measurements, but we'll say that the number of gates in total that you have to do is decreased. So we have this code, and in particular, we need to focus on this logical physical mapping. But first, I'll just say what we get from this. So if we have a QLDPC code that has parameters NKD, the resulting 422 concatenated code has parameters 2NK2D. And again, I have this star here because we need to have an appropriate logical physical qubit map assignment to ensure that we have this 2D distance. So important for our adaptive syndrome scheme is that a significant fraction of the total generators are easy to implement, and that's just due to the fact that they're weight 4, so they're much lower weight than the hypergraph product generators, and they're also embeddable into 2D, which is potentially nice. You could embed the 422 codes together so that you can just measure their stabilizers easily, and then the only non-local operations you have to do is to measure the concatenated hypergraph product generators. And then this last bullet point, we can still perform universal logical computation, and I'll talk about that later. I have slides on this. So let me talk a little bit more about this logical qubit assignment. There's a lot going on this slide. You can, I'll let you look at it for a little bit, but the point that I want to make is that if we want to encode some operator into this 422 code, in particular, if we want to think about the logicals of the hypergraph product code, the 422 concatenated version is going to have logicals that are formed from the iceberg logical operators. So for example, if we have Z1, Z2, Z3 as some logical operator, then that gets mapped into the corresponding Z1, logical Z1, logical Z2, and logical Z3, whatever that may be. And the main thing that I want to point out is that depending on this assignment, given these two tables, the resulting operator can have higher or lower weight. So in this mapping, we get a weight 4 operator, and in this mapping, we get a weight 6 operator. And the thing that we're going to try to avoid is that operators, in particular logical operators, shouldn't have support on more than one logical qubit from the same iceberg block, because then that we get situations where the resulting concatenated logical operator has lower weight than 2 times.
I mean, so Noah, I mean, so this is I mean, if I can ask, related to so in Shore, for example, right? Let's say something similar, like the first codes which was developed. There was a X error you can correct, you can Z error you can correct, similar kind of idea. You concatenate them, now you can correct for both X and Z error. And then the weight of the checks, that got increased. So that was an issue. So then Bacon Shore came and said that, the code came and they said that, I mean, what you can do is that you can develop a subsystem version of the code, and you can reduce the check of, the weight of the check operator that you are interested in. Here, you are taking, like two full-blown codes, like one is detecting code, one is correcting code, and you are concatenating them. And that is again, like, the curse of concatenation, you are getting, like high weight. So, I mean, did you already think of like, doing here, like in this work, I mean, do you do some subsystem thing, or it does not work or something, like, to reduce the check weights or something?
So we didn't think specifically about making a subsystem version. The check weights, so the resulting 422 concatenated code is still LDPC because the iceberg logicals are weight 2, and then the checks of the hypergraph product code are also constant weight. So then 2 times the constant is still a constant. So that's not an issue in terms of LDPC-ness. This specific issue arises from the concatenation scheme that we chose. When you have an underlying code that has more than one logical qubit, then you have to deal with this sort of mapping problem. Like when you do Steam code or surface code or whatever with a single logical qubit, then it doesn't matter what you do because a single block is just a full code. But in here we have a single code block containing 2 logical qubits. And indeed, we want this operator to be large because this is the distance. Like this is the minimal weight logical operator of our 422 concatenated hypergraph product code.
I see, but yeah, I mean, I agree that, like, sure, like there is this theoretical thing, like, LDPC codes, like, constant weight checks, constant number of qubits participating, all that. But then what is that constant that very much matters, right? Like recently, this weight bicycle code came. Sure, constant, weight 6. But then experimentalists won't be happy. They would say weight 5, weight 4. Like, can you reduce that? So like I was coming from that perspective where, like you have some subsystem version where you can, like maybe still protect your distance, and like something similar to bacon shore code, right? I mean, sure, it does not have threshold, but there are main means through which you can ensure threshold. Uh yeah, like maybe that could have helped, but yeah, when
Yeah, I can totally see it. There are subsystem, for hypergraph product codes that could be good. But I think the main thing that we're trying to achieve is that with the adaptive scheme, we're not measuring these high weight hypergraph product generators very often. So when you decrease the error rate, going to 0, a majority of the checks are going to be the iceberg generators. So you're going to end up pretty much only measuring these weight 4 checks. So for an experimentalist, that's, barring gauge operators of some subsystem code, these weight 4 checks is, pretty ideal. So going through this mapping a little bit further, I want to briefly mention that these hypergraph product codes have this canonical logical basis. And really all that means is that in this middle panel, we see these operators, these red and blue operators. They have support on a single row and column of this grid, which represents our physical qubits. And going by the thing I said previously, we don't want iceberg logical qubits to essentially live on the same row or the same column, because in that case, we're going to get a lower weight of our 422 concatenated hypergraph product code logicals. So to accomplish this, we have this specific qubit assignment where we put consecutive logical qubits from the same iceberg block along the diagonal. And we also put them as these mirror or twin qubits. So doing this ensures that, one, the z and x distances are balanced since we have some symmetry there. 2, we also get this full distance of 2d. so we get the most error correction that we can out of the 422 concatenated version. And then also it enables some of these fold transversal gates on the resulting code, which we use later in our logical computation side.
So Noah, if I can ask some so to clarify this so for example, so one iceberg block will be on like this qubit 1 and 8, and another will be on 23 and 5. Is that like what you mean there?
That's right. So there's 4
Okay.
physical qubits encoding 2 iceberg logicals, and
Yeah.
then one of the iceberg logicals is on 1 and one's on 8.
Got it. Thanks.
Yep. Okay, so there's our code. That's how we're going to do all this. So normal vanilla QEC typically goes like this, where you prepare a state, you assume that there's no errors, you correct all the errors in the state, and then you measure all the generators, do error correction, and then you apply the correction. That's essentially it. You might throw some logical gates in there, but this loop continues until you have your logical computation done. So what we propose is this QED plus QEC sort of scheme, where we prepare our 422 concatenated code. And the first thing we do is we're going to measure only the iceberg generators. So in doing so, we get some syndrome information that tells us which one of the iceberg blocks has detected an error. And that allows us to sort of approximately pinpoint where the errors are in our system. So if we, the first case, if we have no iceberg generators flagging, then we can know with some certainty that there's no errors in our system, and we can just continue with our computation, apply logical gates, and do whatever. On the other hand, if we get some flags from some of the iceberg blocks, then we know that there's an error in that block, and we should sort of investigate further by measuring additional additional hyperapodic generators. And after we do that, we can apply the correction, and then we just repeat the entire process again. So pictorially, this sort of representation, we can imagine we have our bunch of iceberg blocks sit together, and then we measure these wait for checks. And suppose we have this one in the top left that flags. So we know that there's an error on one of these 4 qubits. Now in our second stage, the only stabilizer generators of the hyperapodic code we're going to measure are the ones that touch essentially the iceberg logicals contained in this block. So, this one, which is like X2, and then this one, which is X1, same. And we don't have to really think about touching the rest of them because we're pretty confident that there's no errors on them. So what does this mean? What do we get from this? By measuring only the necessary or useful generators, that's going to give us shorter syndrome extraction circuits. I have the star here again because the circuit depth isn't actually reduced, but the gate count is reduced. So we're applying fewer gates, which means that we're going to introduce less noise from these gates and potentially from the less idle. And if we introduce less noise, then we can achieve lower logical error rates. Okay, so that's the scheme. That's how we're going to do it. Now, there's a few small but important points that we needed to kind of iron out to make this thing work. And I'll go through them fairly quickly. The first thing is that when we do decoding, typically decoding concatenated codes works as follows. You first decode each inner code block, and then you convert to either no error or a logical error. And then when you decode the outer code, you get a logical correction, which you apply to the inner code blocks. So you get some, your errors is now in terms of the inner code logicals. Now this is all fine and good, but the 422 code cannot correct any errors. So how are we going to accomplish this first step? And what we do instead is that we're just going to apply the same correction each time an iceberg block detects an error. So for example, if we're trying to correct for Z errors in some iceberg block flags, then what we do is we just apply Z4 as the correction every single time. And shown here, the resulting state is either no error if the original error was Z4, or it's either one or two logical errors of that iceberg code block. So then we can go through in the second stage and correct the iceberg or the hyperwrap product code, normally giving us logical corrections, which we then apply to the state. The other kind of big thing was that in this scheme, there's the potential of iceberg logical errors accumulating. And for this adaptive scheme, if we have a bunch of iceberg logical errors in the system, then these are never going to get caught by the first error detection stage. So then we're never going to measure these higher level hypergraph product generators. So this can yield a buildup of errors and eventually overwhelm our system. And this is shown, we did numerics where on the bottom we have just normal non-concatenated expander codes, and we see some sort of error plateauing as the error rate per round sort of flattens out. As opposed to these 422 concatenated codes, if we just continue with the scheme, never changing anything, then we see that there's this crossing point around, say, 75 rounds, where the larger codes actually perform worse performing than the smaller codes. So we sort of lose our threshold after a while, which is obviously not good. So to solve this, we just throw in this unmasking where we measure all the hyperwrap product generators every so often. So the same sort of scheme, but then every X rounds, for example, X equals 10 rounds, then we're just going to measure all of the hypergraph product generators to make sure that there's no hidden iceberg errors in the system. And in doing so, we again achieve our plateauing. This top panel, we see that they're plateauing now, so we've regained our threshold, and it's the errors aren't building up. So then the final thing that we had to iron out was preventing hook errors. So hook errors are errors that can happen in the middle of a syndrome extraction circuit on the ancilla, which can propagate to a bunch of errors in our code block. Now there are ways to sort of fix this or just completely avoid it using better syndrome extraction schemes like cat states or even Steen error correction, I guess. But we wanted to just use a single bare ancilla, so we have to worry about these hook errors. And you have to be careful about the CNOT ordering when we measure our concatenated hypergraph product generators. So in this first left side, we have an error halfway through the syndrome extraction or halfway through the CNOT gates. Then it's going to propagate to a bunch of iceberg logical errors. So this is, of course, bad because these are undetectable and they won't get picked up in the next round. So instead, what we do is we sort of shuffle up the gates to where we measure the first, or we perform the first CNOT in each iceberg block, and then the second CNOT in each iceberg block. And a hook error in the middle of the circuit is going to propagate to a bunch of single qubit errors in different code blocks. So these are detectable, and they'll be picked up by the next round of error correction. Great. So with that all the way, I'm going to go through our numerical simulations where we did circuit level simulations of this scheme. So we use the circuit level noise where every single action in the circuit can be noisy. So this includes idling error, single qubit, 2 qubit, state prep, and measurements. So we parameterize this noise model with an error rate P, a single error rate P, and this decides, the probability of having error in one of these situations. I note that we have this 0.1 P for the idle error and the single qubit gate. And this is a fine assumption to make because, like I said, on some devices, the single qubits and idling is much, much better than the 2 qubit in measurement. Typically, the 2 qubit in measurement is what's the noisiest. So an order of magnitude better error rate on these two things is a fine sort of practically motivated assumption. So for those who are interested, this is our nitty-gritty simulation details. What we did was 100 rounds of syndrome extraction, and to decode, we use phenomenological syndrome decoding. So even though we do circuit level noise, to decode, we are just doing it based on the syndrome itself. So there's been a bunch of papers where people do circuit level decoding, where you take the detector error model and you correct for space-time errors essentially in your circuit. We don't do that for technical reasons. I guess I can talk about that more if people are interested. But it was essentially too difficult to simulate. So if we somehow figured out a way to change from this phenomenological syndrome decoding, which is essentially you're just decoding this the parity check matrix plus some augmented part of the matrix representing syndrome errors. If you were to change that to circuit level decoding or even sliding window is an easier fix, but both of those would probably improve our results. To decode, we use this BP LSD decoder, this localized statistic decoder, which is just a variation of OSD. And over the 100 rounds, if it's below round 100, then we only do BP. And then on the final round with our noiseless syndrome, that's when we use the LSD. So it's most of the time we're just doing BP. And then as for actual implementation, we do it in STEM. And we have to use the Tableau simulator, again, for some technical reasons of how STEM works. And we do the idling error computed according to the graph coloring of the Tanner graph. So we have some authentic, accurate idling error. So here are the results. Here's the 422 concatenated quantum expander codes. So the first thing we'll look at is this middle panel, which is just the vanilla, normal hypergraph product codes. And as you can see, increasing the code size decreases the logical error rate per round. So that's what we like to see. It's below threshold. And I'd like to point out on the right-hand axis, the right-hand y-axis, I have plotted the average C0 gates per round. So these are these dashed lines. So for example, in this middle plot, we have around 10 of the 4 C0 gates to implement this 936.8 code. So on the right, we have the non-adaptive 422 concatenated hypergraph product codes. So this is the same code that I've been talking about. It's just that during syndrome extraction, we measure every single generator every single time. And you don't actually get much out of it. You get even slightly worse performance for using twice as many qubits and more C0 gates. And this is sort of, could be expected because you're performing more gates and you have more qubits that could have an error, despite the fact that we have this 2 times the distance. Now, on the other hand, left-hand side, we have the adaptive scheme and the 422 concatenated hypergraph product codes. So now we see below some error rate around 5 times 10 to the minus 4, we actually get some pretty nice improvements over the normal hypergraph product codes. And this makes sense because this is essentially the regime where this adaptive syndrome extraction would shine. Because in the low error rate regime, there's not going to be many errors, obviously, and then we're only going to be measuring mainly the iceberg generators. So we don't have to even touch the high weight concatenated hypergraph product generators. We're only going to measure these weight 4 iceberg generators. And this can be seen in these dashed lines where they sort of slope down as we decrease the error rate, because we're measuring fewer generators, and eventually we're just going to be only measuring these iceberg generators.
So by the way, what are the seed codes that you use for the HEP codes here?
Yeah, the seed codes are randomly generated 3-4 codes.
Okay.
Yeah, is that, you need more than that? We just randomly generate classical codes that have column weight 3 and check weight 4, I think.
Okay.
And then we to pick the actual code, then we did some Monte Carlo simulations to pick the best ones.
That sounds good.
Yeah, so you might be saying, you have to go pretty low error rate. 10 to the minus 3 is current error rates. 10 to the minus 4 is pretty optimistic, but some people think that you can get down to 10 to the minus 4 physical error rates. Now, instead, we have these lacrosse codes, which again are these hypergraph product codes, but they're formed from cyclic codes, so they're not as robust, but they've still been studied in some contexts, so they might be useful. And in particular, they perform much better than the non-concatenated, non-adaptive versions, which can be seen by comparing, the blue curve with the green curve, and also the yellow curve, I guess. Really, the point is that across the entire range of physical error rates, from 10 to the minus 4 to 10 to the minus 3, we're getting at least an order of magnitude performance out of these codes, which is pretty good. And to achieve the same sort of performance out of the non-concatenated codes, then we need significantly bigger codes. So, on the right side, we're using maybe 8 times as many qubits to even approach this green line. So to sort of show this in a different representation, we plot the physical qubits versus the logical error per round for a variety of physical error rates. We see at low error rates, this p equals 0.1%, that the green curve, these iceberg expanders or 422 expanders, they perform better than the blue curves, and we just threw in surface code. But as we increase the physical error rate to even 0.05%, then it's less obvious about which is the better. And at 0.1%, the expander codes, non-concatenated, are performing better. On the other hand, for the lacrosse codes, the 422 concatenated lacrosse codes, we see better performance across the entire range of error rates. So there is a significant benefit to using these codes, no matter how the physical error rate is. Great. So we've shown that they can function pretty well as logical memories, and they can outperform their non-concatenated, non-adaptive versions. And we've also seen that they sort of can reduce the C0 gate count, which is nice. Now, we also show that we can do universal logical computation with these things. So in particular, the 422 code has some nice transversal gates. And in this 422 concatenated code, some of these come in handy when we're performing gates of the logical gates from the concatenated code. In particular, these C0 gates and these swap gates are just swaps on the physical qubits. So these can be implemented really nicely. And by assigning the physical or the logical qubits in the way that we did with the along the diagonal and mirrored, then we can apply some of these fold transversal gates on the 422 concatenated hyperoperonic code directly and not have too much additional overhead. So I'd like to, I guess, first of all, these are the sort of things, this is a list of gadgets that we need to have to perform logical computation, at least Clifford logical computation. So you need state prep, measurements, C-knots, Hadamard's, S-gates, and logical translation. And then you also need these recently introduced concatenated grid poly product measurements, which are modified from this recent paper, Fast and Parallelizable Logical Computation. So these, the first gadget and the third gadget, the state prep and these grid poly product measurements were our sort of main troubles in translating existing hyperoperonic code literature into these 422 codes. And but eventually we got them all inherited. So in particular, we showed that they have this single shot state prep, which is based on this recent work by Han for hyperoperonic codes. And in short, he showed that if you start off with essentially a 3D hyperoperonic code, some homological product, three-dimensional homological product, then you can get single shot state preparation, which is before this not known for hyperoperonic codes, just by using the soundness of the 3D code and then performing essentially space-time decoding on the resulting measurements. So to port this over to ours, we had to show that our 422 concatenated codes had good soundness and confinement, and so that's what we did. So now what we can achieve is that we can trade space for time, or trade time for space, where instead of measuring d times, we use order d extra qubits to do this single shot state prep. So then the other thing we had to sort of port over was this grid poly product measurements, which is essentially a method for measuring products of polys. And in this diagram is the schematic for how this sort of scheme works, where we have a number of hyperoperonic codes, some ancilla blocks, and we're performing transversal C0 gates between them. And in some of the ancilla blocks, some of the rows and columns are punctured, which allows us to target specific logical qubits in our data block to measure. And this can be used to perform a bunch of measurements, but also some gates in these codes. So the difficulty here was, if we want to puncture these ancilla blocks, it's kind of difficult if we were to use a 422 concatenated code, just based on the assignment of logical qubits that we did. But we showed that we can use this physical logical mapping circuit here, I guess, or the C0, logical physical C0, which allows us to just use normal hyperoperonic codes for the ancilla blocks, and we can couple them with our concatenated data block, achieving the same sort of measurements and gates that were possible before. So in doing so, we show these two theorems where we can get, if we want to simulate some k-qubit Clifford circuit with ordered k gates, then we get these time and space costs. And then if we have specific these like special hyperref product codes with this one generator systematic circulant property, then we can either reduce the time cost or reduce the space cost. All right, so in conclusion, we've introduced this adaptive syndrome extraction scheme, which uses this QED plus QEC sort of pipeline to approximately locate errors before performing full expensive quantum error correction. And we showed an explicit example of this code using, or this scheme using a 422 concatenated hyperref product code. Through circuit level simulations, we showed that in quantum memory, we can achieve lower logical error rates and fewer CNOT gates. And I'd like to mention that for certain architectures, specifically architectures that can't really implement very many CNOT gates in parallel, like ion traps, then decreasing the CNOT gate count actually shortens the wall clock time of the quantum computation. And then finally, we showed that we can modify previously developed hyperref product code logical computation schemes for usage on our concatenated code. So we get the best of both worlds, where we didn't have to suffer any slowdowns compared to unconcatenated versions for logical computation, but then we also get this benefit of this adaptive scheme. So for future questions, I think there's a lot you can think about. I think there's a number of immediate things that you could try. In particular, you could just throw some different codes at it. You could try using different iceberg codes. Your error detecting code block is bigger, so maybe you can slim down on the number of generators you have to measure in the first round, or you could try different QLWC codes for the outer code. We chose hyperref product codes because they were well studied and they have nice existing literature about them, but you could try using bivariate bicycle codes or really anything you wanted, probably. There might be an alternative concatenation scheme which works for this. The scheme that I mentioned before had this issue with the physical logical assignment, but if you use the other concatenation scheme, it kind of avoids this. Maybe you could achieve adaptive syndrome extraction without concatenation using some sort of heralded error or some other method of detecting errors. Can syndrome extraction speed up decoding? Potentially. Maybe we can achieve faster logical computation with more recent improvements in magic state distillation or even other Clifford logicals. And then finally, I mentioned these two applications in the paper, but it could be useful in 2D local implementations of high rate codes. So like I mentioned before, if you embed it into 2D, you can have these 422 codes local, and then the only non-local interactions you have to implement are the hyperref product code generators that we measure only frequently or infrequently. So it could be useful for that. And then similarly, we could maybe try using this on modular QPU architectures where we have a bunch of quantum computers hooked up by photonic interlinks, and we want to avoid using the interlinks because they're, for example, noisier. So we can apply the scheme on each QPU individually and then try to use the interlinks less frequently. So with that, I'll end it here, and thank you again for listening. I'm happy to take any questions. Here are my lovely collaborators.
Yeah, thanks, Noah. So if you have any questions, please unmute yourself and ask.
So I just have a question about the first point in your future work slide about using bigger iceberg codes. What about using a smaller one like 312 error detection code or something like that? Like so you have like one block for each qubit in the I don't know, hypergraph product code, for example.
Yeah, that could work. The 312 code could work. Your I mean the rate's a little worse, I guess, than the 422.
Well, yeah.
But you might avoid some of the issues with having multiple logical qubits per block. So yeah, you could certainly. I think is the 312 code the smallest? Probably the smallest.
Yeah, I couldn't think of there
Yeah,
could be
yeah,
any
but
smaller one, but yeah.
but yeah, that could totally work.
No, I'm just thinking like what would be the downside? I mean, okay, like the encoding rate would go down, but you know, like otherwise it everything should work just fine. I'm not sure. And you don't have to do like this mapping stuff that you did earlier, right there.
Yeah, you wouldn't have to deal with the mapping, so you'd immediately achieve the full 2D distance. I can't see any downsides right now. Maybe I could see that logical computation is harder, because these 422 codes have, quite a few nice gates that made logical computation pretty easy. I don't know how you can do it on 312 code, but I assume it's probably a little bit harder.
Okay. And also, probably I'll ask question about the so you mentioned like there's like this difficulty with simulating you know the circuit level noise stuff. So so is that like just because like the circuit's too big or
No, so the limitation in that case was the way STEM works really is you pass it a circuit and then it'll compile it down into like a detector error model essentially, right?
Yep.
And then when you want to do simulations on it, you just essentially pull from this model and it'll give you shots
Yes.
of detector data, which is fine. But the issue for us is that in the middle of our syndrome extraction circuit, we need to make decisions. So we can't compile a circuit down to this detector error model. We need to actually be looking at the measurements that that happened and then make decisions based on that.
Right. So does that mean like if you want to use like that the detector error model from STEM, you have to simulate all the possible choices that you could make, or is that kind of like
Yeah, I probably wouldn't do that. I tried. Essentially what you do is you do an entire run and then that gives you a circuit, right? And then you can pass that circuit into STEM,
uh-huh.
Which gives you a detector error model. And then you also have the syndrome data that you recorded throughout that run. And you can use that syndrome data with that singular, with that, detector error model that was just generated to get one shot. But you have to do that on a shot per shot basis. You can't like compile anything down because the circuit is different every single time.
Yeah, okay, that's interesting.
Yeah, I mean, Steam has like, I mean, yeah, like resistance. I mean, not limitations, but currently like not written in that manner. Yeah. So thanks, Noah. I think it's 11, and I will stop the recording and yeah, like thanks everyone for joining and see you next week. We have like I mean, another talk. So let me stop the recording now.